All right, so as promised, let's look at some sims here. This is, and these are all on canvas, by the way, as well, as always. Masses and Springs, PHET sim. How this works is, I'm going to actually go back to the intro here for a second to get this a little simpler. Natural length. This is if you were to hang. Now these are springs just kind of hung from the ceiling or whatever. This is where they would be after you kind of got them to stop oscillating. And gravity's going to stretch them out a little bit, not a whole lot, but enough to where we have a natural length there. And then equilibrium position. Right now, that's the same. But if I take this 100-gram weight and put it on there, now I have now that equilibrium position changes, because if you'd imagine, once this thing stopped going, and by the way, I have in this one, damping is 0. Damping is basically just like friction in a spring. Eventually we know that, in real life, if we had something like this, it would kind of settle in. It would settle that in because of damping. But in this case, we have eliminated damping, so this green is where that would settle in to its equilibrium position. So if I slow this down, we can see it oscillating about this green line right here. Now notice I can toggle gravity. So right now we're at Earth's gravity. But what would happen on the moon? I think more or less. A little bit less, because we have less acceleration due to gravity that is pulling this object down, so therefore it's going to oscillate a little bit closer to its normal there. What about Jupiter? Well, we already saw that Jupiter has more gravity, so yeah. Okay, yeah, that's a lot. Now this does kind of carry over too, so like if I took this back down to Earth, it's still going to oscillate a little bit wildly, but you can kind of see the effects there. Now if I go to vectors here, it's going to allow me to see a little bit more of what's going on. So I'm going to do that same thing right here and really slow this down to see what's going on. So displacement, natural length, so we can see this is kind of that natural length area right here. And we can see the interplay between the force of gravity, which is constant because it's just dependent on the weight of that 100 grams. There, 100 grams times 9.8, because we're on Earth right now. And then the spring, we can see the force of the spring increases as we get farther from equilibrium there. And then, sorry, just allergies, I promise. Acceleration, we can see the acceleration moving back towards that equilibrium. Soon at the point, let me see if I can pause it right over equilibrium. Yeah, that's pretty close. We can see when it's at equilibrium, like you saw in the Bozeman video, we don't have any acceleration. So that's really cool. Okay, so Hooke's law. We mentioned Hooke's law in there. So this is a really great illustration. Let me, yeah, it's reset. So what this means is with a spring constant of 200 newtons per meter, I can kind of slide this over, and as I apply that, oops, let's get the rest of this here. As I apply that, as I compress this spring, if I want to achieve a certain displacement, I have to continue to put pressure on it. So 100 newtons of force, and also notice that there's an equal and opposite reaction there. The spring is pushing back on here at 100 newtons. Now, if I increase spring constant, what do you think is going to happen? Increase the spring constant with that same 100 newtons, I get less and less displacement, because again, we go back to F equals kx. Now, the greater k with the same force, it means I'm going to have less distance there. So again, you can try these on your own as well. And this is a pendulum lab where I can kind of set this up to swing like that. And right now I don't have any friction going on. And you can also, I'm not going to do too much on this, but you can do a period trace and So about 1.6 seconds. You can kind of apply this to the formula to do that. I'm going to move on to this next one. This is not a PHET. This is another thing that I found. I'm going to go ahead and get this started. This is kind of simple harmonic motion. See this spring going in and out, but it has damping. It also has a graph function to it. So you can see the circular graph is kind of showing the motion of this. And you can see as it slows down, you can kind of track each of these movements here. And then multi-graph there. So you can see as it's damping, you can see each of these kind of get smaller and smaller. So again, this is something that you can kind of try out on your own. I'm going to try to keep these videos as brief as possible. So I am going to move on. Sometimes my computer really gets on my nerves. I'm going to move on to the first classwork here. I'm going to kind of do it like I do in class, give you the first classwork problem to look at and let you kind of do the rest of them. So a block of 2 kilograms is attached to the free end of a certain steel spring with constant 72 newtons per meter, which hangs from the ceiling. So it's kind of like, let's go back to this one. It's kind of like this right here. We have this hanging from the ceiling like that. No, I don't want to show that yet. This is going to be a little clunky to begin with. Determine the period with which the mass bobs up and down. So in other words, down, up, and then back. That's the period. What amount of mass added to or subtracted from the block would result in a doubling of this period? Okay, so to start with, so we just want to list our variables here. We have a mass of 2 kilograms. We have a spring constant of 72 newtons per meter. Well, we could just plug that right into the problem here to get the period. Just 2 pi times the square root of m over k. M is 2, k is 72, and then we have that gives us a period of 1.05 seconds. Now, for the second part of that, so for part B, again, what amount of mass added to or subtracted from the block would result in a doubling of this period. I kind of approach this from just a variable standpoint where, okay, I start with this, and then, okay, if I make this 2, because I want to double because according to B here, I'm wanting to double the period. Okay, so proportionally, if I double the period, well, I have to double what's over here as well. So 2 times 2 pi over the square root of m over k. Well, working that out, or just kind of rearranging that really, I can algebraically rearrange that to say 2 pi times 2 times m over, or actually I think I kind of skipped a step here. So 2 times that, so basically I'll just let you work that out. I kind of looked at this earlier, but if you work that out algebraically, you will get that doubling the period results in quadrupling the mass there. And you can actually work that out with some numbers too. I did this kind of off to the side. Like, say you start with a 4 kilogram mass with the same 72 Newton per meter spring constant. You would get a period of 1.48 seconds in that case. And then if you double the period in this case, which would be 2.96 seconds, you end up with a mass of 16 kilograms. So again, that shows that relationship of doubling the period quadruples the mass. So you kind of get a little bit of an exponential process there. All right, so I gave you answers for 30, 31, 32, and 33. 34 kind of depends on being in class. I loaded that up to Canvas yesterday, so you can use that to check answers. Guys, give me some feedback. Let me know if you have any questions, and I will be providing some more of these pretty soon.